Well, hello, ladies and gentlemen. Mr. Dorfler back here with another installment of the Daily Dose of Dorfler. All right, here we are on to section 2 of chapter 5. In the first section, we got to see quite a bit of definitions, a couple of formulas, okay? And we're going to continue building on that idea of some of the things that we saw, okay? Today, we're going to be looking at the first law of thermodynamics, a couple small things there, and then we're going to shift our attention in this section to the concept of system and surroundings, but also tying in energy in forms of heat and also work, okay? And so I'll kind of elaborate a little more when we get into those sections. We're going to start, I'm going to round out the discussion today talking about what's known as a state function. Okay, we're going to identify what falls into the category of state function and what doesn't fall into that category. So let's look at the first law of thermodynamics, okay? Really, we get a visual representation of this, okay? Loss of energy from a system points downward. And so when we have a loss of an energy of a system, we see that our final energy is going to be lower than what it initially was. And then when we have a gain of energy by a system, we're going to see that this red arrow is indicating that our final energy is going to be higher than the amount of thermal internal energy that we initially had, okay? So internal energy of a system, again, our main focus is really going to be the system, okay? Our concern is, what is the system doing? What is the system having done onto it? Is it absorbing or releasing energy? Okay, so our real focus is the system. So back at internal energy of a system is the sum of all kinetic and potential energies of all components of the system. We call it E, okay, capital E, in fact. By definition, the change in internal energy, or delta E, the delta sign here just means change in, is the final energy of the system minus the initial energy of the system. So kind of get an idea of what we're going to be looking at, okay? How does it, after something happens, what does the internal energy look like compared to how it started? So we have a couple scenarios. If we have a change in energy where the final energy is greater than the initial energy, so the system has gained internal energy. In this scenario, the system has absorbed energy from the surroundings, okay? Well, energy being absorbed, you take in energy, you're going to have more energy there. So our final energy would be greater than our initial. When this process happens, this energy change is called endergonic, okay? There's going to be a handful of terms that we're going to see today that are going to be very similar, but we don't necessarily focus our attention on these first two as much as our second two definitions, but it's still a very important term here, okay? This change in energy, when we have an increase in internal energy, it's an endergonic process. System absorbed energy. If we have the exact opposite situation occurring, where we have the final energy of the system is going to be less than the initial. Excuse me. What this means is, choked, the system released energy to the surroundings. Okay. In yesterday's discussion, we talked about the system and the surroundings, and we used that example of the gases inside of a cylinder that had a piston on top of them. Okay, and the system was what we wanted to study, and that was the gas molecules. Okay, so if we have a final internal energy that is less than our initial, we have released energy to the surroundings, and this is called an exergonic. So let's think about this: endergonic and exergonic. When we have an endergonic energy change, we have energy going into the system and being absorbed. Endergonic kind of sounds very similar to into, okay? Same thing we can do with exergonic, okay? When we have final energy lower than the initial, then energy has been released to the surroundings. So energy is exiting the system to the surroundings. Exorganic, exiting. See where I'm going with that? Okay, these are simple ways to break words down to help us remember the definition. So when we talk about changes in internal energy, think of it as kind of like a bank account, okay? So your system and the surroundings are like a bank account, okay? The inside of the vault is our system, okay? That's where our money is. The vault itself is the surroundings, okay? And so when we take a look into the changes of internal energy, there's really two things that we need to look at: heat and work, okay? When energy is exchanged between the system and the surroundings, it is going to be exchanged as either heat or work. And we denote heat with the lowercase q and work with the lowercase w. So really, mathematically, we can solve this by taking a look at this simple formula here. Delta E, so your change in energy, is equal to Q plus W. Well, let's look at some other examples here. So if we have an endergonic situation where we have the system, or money, absorbing energy or taking more money in, we see that our bank account has gotten much larger. Or if we talk chemistry-wise, the internal energy has gotten larger. And this happens when we have heat gained and work done on the system. Okay, those are all positive values. Heat is positive and work is positive. We see an opposite situation occur. We see our bank account start to shrink. So we see our internal energy shrink when heat is lost by the system to the surroundings and the system does work on the surroundings, okay? So if heat is lost and work is done by the system onto the surroundings, both of those values are going to be negative. Now, it's very important when we look at situations when we are calculating change in E and trying to determine our Q and our W, that we pay careful attention to sign conventions, okay? Table 5.1 is something that you really need to pay attention to. Okay, let's look at each individually. If we have Q, let's do line by line. If the system has gained heat, and it should be fairly obvious when we start looking at practice problems here as whether something gains heat or loses heat, okay? If something gains heat, you give it a plus sign. If something loses heat, that means the system is going to have a negative sign, okay? That means heat would have a negative sign. So if it gains heat, you get a plus sign. If it loses heat, you get a negative sign for the value that you're given. Again, it's all about the system, okay? What's happening with the system? For work, W, again, positive sign when work is done on the system, and negative sign when work is done by the system. Because it's going to take some reading of the question to really finalize what signage we're going to use for our values. After we've determined Q and W, what signage they're going to have, we go ahead and solve for that. And then in the very end, when we solve for delta E, if we have a positive sign, that means there is a net gain of energy by a system. So it was endergonic. If there is a negative sign for delta E, that means there was a net loss of energy by the system. Therefore, it's exergonic. Okay, let's take a look at two examples here. Okay, first, let's look at what we are given, what's worked out for you. So we have gases A and B confined to a cylinder and piston arrangement like in figure 5.4, like the figure we saw in section 1's discussion. They are going to react to form a solid product of C, okay? So as the reaction occurs, the system loses 1,150 joules, again, joules is our unit for energy, to the surroundings. The piston moves downward as the gases react to form a solid. As the volume of the gas decreases under the constant pressure of the atmosphere, the surroundings do 480 joules of work on the system. What is the change of internal energy? So let's first figure out what values we're given, who they belong to, and what signs do they need, okay? Again, we're using the very basic equation of delta E is equal to Q plus W. Okay, first we're given that as the reaction occurs, the system loses 1150 joules of heat to the surroundings. So the system loses heat. Ask yourself, would that make Q be a minus or a plus sign? Well, it says the system loses heat to the surroundings. Whenever heat is lost by the system, it gets a negative sign. So we'll have a negative 1150 joules. Now let's look at work. It says the surroundings do 480 joules of work on the system. Anytime that work is done on the system, work will be a positive sign. So we have a plus 480. So once we've determined our signage, we go ahead and put them into that equation and calculate for delta E and determine what type of energy process is going on. So again, we have delta E equals Q plus W equals negative 1150 joules plus 480 joules, and we get an overall change in energy of negative 670 joules. So what that negative sign tells us after our calculation is done is that there is a net loss of energy by the system. And since it is a net loss of energy and it's got that negative sign, that means it is an exergonic process. Okay, because again, it's exiting the system. Let's move on to the practice question here. Okay, so if you want to get a piece of paper or a calculator, by all means. Okay, it says calculate, we're down here, the change in the internal energy for a process in which the system absorbs 140 joules of heat from the surroundings and does 85 joules of work on the surroundings. Okay, so going back to the problem here, it says the system absorbs 140 joules of heat from the surroundings and does 850 joules. So let's talk about the Q. Let's talk about heat. It says the system absorbs 140 joules of heat from the surroundings. So since the system is absorbing it, that means it's a positive 140 joules. Now for W, it says that the system does 85 joules of work on the surroundings. Okay, so thinking about what sign to apply to that, since the system does work onto the surroundings, that must mean it's a negative 85 joules. Okay. Oops, I can't even write a little Q. So setting up our equation Q plus W. So we go ahead and just put in our values. Q, again, was 140 joules. And work being a negative 85. Sorry, I got sidetracked there. Joules. Sorry, my handwriting still hasn't come up to snuff here for the semester. A little rusty here. So once we've got that in there, we go ahead and calculate that we actually have plus 55 joules. So since we had a positive 55 joules, we had a positive sign, meaning that was a net gain of internal energy. Therefore, the process was endergonic. Okay? So that's that. That's how we determine. Okay, it's very important to determine the signage for your Q and W. That's really where you're paying attention and reading of the question is going to come into play. All right, so that's it for calculating internal energy. Not too bad today. Have a few more slides to go, so bear with me. Here are the two next terms that are going to be probably more prevalent than endergonic and exergonic. Okay? And we're talking more specifically about heat in this case. Okay? Before, when we were talking about endergonic and exergonic, we were just simply talking about energy. In this situation that we're getting ready to talk about, we're more specifically talking about heat. Okay? When heat is absorbed by the system from the surroundings. The process is endothermic. Now, what's really interesting about this, okay, when a system absorbs heat from the surroundings, you would imagine that the system would be warm since it's absorbing heat. In fact, the contrary is true. So, well, let's think of it this way. When heat flows from the surroundings into the system, okay, the temperature of the surrounding drops. The thermometer is actually going to read temperatures well below room temperature in a reaction, okay? So again, when a system, so in here, in this example here, in this system, the system is going to absorb energy from the surroundings. So if we were to put a probe into the surroundings, which the surroundings are actually the solvent. So this is where it gets a little tricky, okay? Let's just define everything here. Okay, so in this system here, or in this scenario, we have reactants and products inside here. Okay, they are aqueous. Okay, so the surroundings themselves are actually the solvent. Okay, most likely water. Okay, so you have water, then you have the solutes inside there, which are the reactants and the products. So the system, which is the reactants and the products, they absorb heat from the surroundings, which is the solvent or the liquid water. So as that reaction is taking place and products are being formed, the surroundings, the water, are actually losing heat and feel colder. Okay, that's the whole process of an ice pack. If you've ever had to use an ice pack, whether sport related or work related or whatever, okay, at first you feel that ice pack is just kind of at room temperature. Well, as you fiddle around with that ice pack and you break whatever contents are in there, the system, which is again the reactants, they begin to react and form products. Well, that is causing the liquid, which is again typically water, to maybe another solution, another solvent, but again, that causes the heat from that surrounding liquid to be lost and absorbed by the reactants in the system that is happening. That's why it turns solid into solid ice, okay? Because that reaction has absorbed so much of that energy, that heat energy from the liquid water. And that's how you get an ice pack. When heat is released by the system into the surroundings, we get what's called an exothermic process, okay? Again, much like we saw with the endothermic or endergonic and exergonic, when in this process, when heat is absorbed by the system, it's going into the system, and when heat is released by the system, it is exiting the system, okay? So if you look at this example here, the system, again, is the reactants. The surroundings is simply the air around the reactants, okay? Heat flows, and oftentimes exothermics are somewhat violent, not all the time, but a lot of times, from the system to the surroundings. And in the surroundings, we're going to see an increase in temperature, okay? Another example you might have is one of those hot hands, okay? If you've ever been outside in the cold, hands get really cold, or even your feet, or even your body now. They've got all sorts of different hot hands now. Anyway, hot hands have chemicals inside there. So once you kind of expose them to air, they begin to react. Others have a little piece of metal in there that react with whatever solvent it's in. But either way, the idea is the same. The reactants release heat energy into the surroundings. And the surroundings are going to be the air as well as your hands. And that's why it feels warm. It's because it is releasing energy to you. It is hotter than you are. So therefore, as we saw in yesterday's discussion, heat goes from areas of high temperature to colder temperatures. Okay, that's how it flows. So that's examples of exothermic and endothermic reactions. You probably use both. The last things we're going to talk about are state functions, okay? A lot of times we don't know the internal energy of a system. It's very complex. It oftentimes isn't necessary. But we do know that the internal energy of a system is completely independent of the path by which the system achieved its current state. If we look at the example down here, so let's just say our current state of water is room temperature, 25 degrees Celsius, okay? We could have reached that temperature of 25 degrees Celsius in more than one way. We could have taken boiling water, okay, and set it out into the room. And so once that boiling water was set into the room, no additional energy is being added to it. It cools down to room temperature. So it had to cool down. So that system had to release energy to the surrounding area until it had the appropriate internal energy, which is the room temperature. Or we could have taken a beaker just of ice cubes, okay, which is frozen water. We could have then again let those ice cubes sit out. And the heat from the room is going to be absorbed by the ice, which is the system. Eventually, that ice is going to melt and the room temperature is going to bring up the water temperature to 25 degrees Celsius. And so it doesn't matter if we start off by boiling it or having it frozen. By letting it sit out, not providing any other heat energy other than the room, okay, it's eventually going to come to what I would consider an equilibrium, a balance, okay? And so, again, it's completely independent on the path at which we got there, okay? It doesn't matter. We just know that this particular sample of water has a certain amount of internal energy. And I apologize, that's First Tuesday. So therefore, internal energy is a state function. Delta E is a state function. It depends only on the present state of the system, not on the path with which the system arrived at that state. So what we really only need to worry about is the initial and the final internal energy to determine our overall change. Okay, so that's important to know. Internal energy is a state function, delta E. And so earlier in this discussion, we also found out that heat and work, or Q and W, are determined and summed up to calculate our change in internal energy, okay? But Q and W are not state functions, okay? Even though delta E is, Q and W are not. If we look at this example here, we've got a battery in two different scenarios. This battery in A is just simply going to be given a short circuit. It's going to have a wire connected to both ends. There's not going to be what's called a load to help dissipate some of the heat. And so it's just going to go and lose energy only as heat, okay? But again, remember, these are identical batteries, all right? So they're going to have the same amount of energy to start off with. In part B, we have it connected to a fan. So as this fan is connected to the battery, the energy of this battery is going to be lost both as heat and work. You know, again, as the energy flows through here, machinery moves, causing heat, but it's also moving. So therefore, we can define it as being worked, okay? So objects being moved by energy, okay, that's called work. So here we have energy lost by both heat and work. In A, we simply only have energy lost by heat, because when you short circuit something, it becomes hot. Okay, but nothing is having work done onto it because there's no object being moved. But if we were to look at this in the form of a table, okay, the same amount of energy by both batteries that is lost is going to be the same. Okay, because since they contain the same amount of energy initially, they're going to lose the same amount of energy when they're completely empty of internal energy. But in A, it's only lost by heat. In B, it's only going to be lost by a little bit of heat, and the rest of it's going to be lost in work. But overall, the same amount of energy is going to be lost. putting into, justifying what we just saw. It doesn't matter the path with which the energy changes, just we only need to worry about the initial and the final amount of energy as it changes, okay? We don't care if it's only lost as heat, and we don't care if it's lost as heat and work, okay? The same amount of energy is going to be lost no matter what. That's why Q and W are not state functions, okay? Because it really doesn't matter on their end. It doesn't matter if we have all heat or all work or vice versa, okay? It all depends on the start and the end. So delta E is a state function. Q and W are not. And so with that concept of state functions, I'm going to call it a day on section 2. Okay? So, again, be working on your problem sets. You'll be having a quiz at the start of next week. Again, we're going to be covering section 4 by the end of this week, but section 4 will not be on this first quiz. It'll only be sections 1, 2, and 3. Okay? Just make sure you check Plan Book, because in Plan Book I have indicated what problem set questions you need to work on and have completed by the time the quiz comes up. So make sure you pay careful attention to that. Anyway, I'm calling it a wrap on today's video. Have a good day, everybody. We'll see you later.